We start our second talk today by Nikolai Kosmatov, Prove Your Coloring, Formal Verification of Cache Coloring of BAO Hypervisor. Thank you very much.
Thank you. So good morning, everybody. This is a joint work with my colleagues Axel Ferriol and Laurent Corbin at Thales Research and Technology, which was initially presented at FACE at ETAPS this year in May in Hamilton. So, and it was done at Thales Research and Technology. So maybe you don't know, Thales is a big industrial group present in many countries with over 70,000 employees working on different domains: digital identity, security, defense, avionics, space. And recently, we worked very intensively on formal verification of the Java card virtual machine with my colleagues listed here. Just to give you an example of a formal verification project at Thales, our goal in this work was to realize formal verification for common criteria certification, which is expected for smart cards. So if you don't know, Thales produces 2 out of 3 smart cards distributed in the world, which include, for instance, digital identity, passports, identity cards, driving licenses, and other types of cards. But you have also similar smart cards in similar devices in your mobile phones, in cards for cars, and many others. In common criteria certification, the highest level, EL7, requires formal proof of correctness and security, and it is what we tried to do in this project. And for the first time, we worked on the real-life code. So we managed to apply our formal verification approach on the real-life code, while in previous approaches, it was done on higher-level models, which is not acceptable anymore today. So the certificate was developed by the French certification body, and it was only one of the few certificates of that level, EAL7, developed out of many certifications. But today I wanted to talk about our recent work, which is on the formal verification of the BAO hypervisor, which is which focuses on the cache coloring module of BAO. So I will start by talking about our motivation. I'm sorry, there is a big delay, so I'm a bit confused. So what is the motivation of this work? Today, hypervisors become relevant for embedded systems to enable more functions, because one cannot add more and more hardware anymore. So for different constraints, size, weight, cost. And that is why hypervisors become relevant to add more functions, in particular for artificial intelligence, entertainment, others, where different levels of criticality of software might be combined on the same hardware. And static hypervisors are relevant in this context because they allow partitioning of resources. So static hypervisors are based on partitioning of resources. They don't use scheduling of different processes, different VMs. And in this approach, each VM has access to its own resources. But some resources must be shared, such as last level cache of processors. And this cache being shared between several cores, each core possibly running a different VM. So to avoid problems with related to last level cache. Cache coloring is used to split cache into several areas, each associated with a color, so that then in the simplest case, each VM is colored with a color, and the data of this VM can only go to the cache areas of that color, which ensures isolation of the cache areas between different virtual machines. So it is a relatively complex and critical module, and its correctness is important to verify. That's why in this work, we decided to work on formal verification of the cache coloring in BAO, which is a static hypervisor. And in my talk, I will present first. Okay. The pharmacy verification platform we used in this work, then the implementation of the cache coloring in BAO hypervisor, the bugs we found and the corrections we proposed, a summary of verification results, a few highlights on our verification approach before giving a conclusion and some future work. So, as you might know, pharmacy is a deductive verification, is a software verification framework which is based on a common kernel and different plugins around this kernel. It offers a specification language, which is called ACSL and CC specification language. And in this work, we will mostly use the deductive verification plugin WP, which is based on biggest precondition calculus, which allows the proof of semantic properties of programs, which performs modular verification, function by function. It takes as input a C program annotated in ACSL and generates verification conditions or proof goals, which are then sent to automatic provers through Y3, like AlterGo, Z3, CVC5, or many others, or interactive provers. In particular, the proof assistant ROP can be used to prove some properties which are not proved automatically. There is also interactive proof capacities inside the plugin itself. And we also use the value analysis plugin ever based on abstract interpretation. So what now, a few words about cache coloring in BAO. So BAO is a lightweight open source static hypervisor for embedded systems, which provides a strong isolation between virtual machines and real-time guarantees. So as I mentioned, we decided to focus on the implementation of cache coloring because it is critical and important to ensure security of the whole implementation. So in this approach, a color is assigned to each memory page. So we talk about cache coloring, but actually it is mostly about page coloring, in fact, because in reality, cache areas are colored just in a way, but most of the time the module will work with pages. So then the idea is that a color is assigned to each memory page and each cache area, so that the data of that memory page will necessarily go to the cache area of that color. I will skip technical details. It is not really very important to understand what happens in the talk. Yeah, as I said, data of a memory page will go only into the same color in cache. And colors can be also assigned to virtual machines, so that if a virtual machine gets some color, or for simplicity, we can say one color, in reality, it can be generalized to have several colors. only pages of that color are assigned to the virtual machine, can be allocated to the virtual machine. In this way, a virtual machine cannot access data of other virtual machines, and in cache, data are also isolated between different machines. Good. So how do we proceed? How does the implementation proceed actually? So the colors are, the pages are organized in periodic blocks of colors, like it is shown here. In this example, we have, for instance, 4 pages for yellow pages, then for red pages, then for blue pages, then for green pages, and then this block is repeated again and again and again. So basically, pages are colored by periodic blocks. We have color size pages of the same color consequently, and we have color num groups of colors in a periodic block, and then this block is repeated. So it is how the pages are colored in this implementation. And actually, the implementation was quite elegant and original, but it was never described. And to describe in our paper, first we decided to somehow formalize what happens in the implementation to explain how it works. And we introduced this notion that we called episet, which corresponds to how it works in the implementation. So what is episet? Episet is a set of n free consecutive suitably colored pages for some color or set of colors. So what does it mean? It means that during the allocation, we will have to find not only one page, but often several pages, and the implementation choice is made to consider consecutive pages of the same color, which are 3. So the implementation will actually look for a set of n 3 consecutive suitably colored pages, and such a set is called a p-set in our paper. So for example, so why the implementation does that? Because in this case, if we know the first page of a p-set, we are able to find all other pages. We don't need to keep the references to all pages. If we know the first one, we just take the second page of that color, then the third page, and so on, and we will be able to find all the n pages. So here are some examples. For instance, pages P2, P4, P6 form a p-set of size 3 for the yellow color. P2, P4, P6, indeed, they are yellow, consecutive, and free, so it is indeed a free p-set of size 3. P1, P3, is it true that it is a p-set of size 2 for blue color? If we look into P1 and P3, we see that indeed they are blue, they are consecutive, but P3 is not free. So it is not a free p-set for the blue color. And if I take P1, P5, P1, P5, they are free, blue, but not consecutive. So I don't want such a p-set. So that is just to give you a few examples. So now, when we define this notion of a p-set, what are the bugs we found in the algorithms? So, for example, on this toy pool of pages, if we try to allocate 2 free consecutive blue pages, when the starting page is P7, it is another technical detail. In fact, the implementation considers that the new allocation shouldn't start always from the beginning, because maybe previous allocation started somewhere in the middle. So it is better to start where the previous allocation stopped, and we have more chances to find free pages from that moment. So if the previous allocation stopped at P7 here, and we start a new allocation of 2 pages, it happens that a wrong result will be returned, which will be P1, P3. P1, P3 to find 2 free consecutive blue pages. And of course, we see that the problem is that page P3 is already occupied, is already allocated, possibly to the same VM or another VM accepting the same color, which is a problem, the first bug we found in the implementation. And to be sure it was not our wrong understanding of the code, we also confirmed this counterexample with the value analysis plugin ever of Pharmacy. Another bug we found is that consider this example of another pool of pages, which are occupied. If we allocate a set of 2 free consecutive blue pages, starting from page P1, it happens that the implementation will allocate pages P5, P7, P5, P7, and page P7 has already been allocated, again, possibly to the same VM or another VM accepting the blue color. And in a variant of this example, if we have only 6 pages in our pool, it will be still P5, P6, which will be allocated, and page P7 can be even non-existent or occupied by the hypervisor or another virtual machine. This counterexample was also confirmed. So, of course, we reported those bugs to the implementation, to the developers, and our corrections were integrated. And what is interesting is that those bugs are present in the code since 2020, since the initial commit of the code, but now they're fixed. We also proposed some further code optimizations in the paper. But let me now talk about our verification results. So, okay, after fixing the bugs, the main goal was, of course, to verify that the implementation works correctly. So we considered the key functions of this cache coloring or page coloring module, and also to check the consistency of our contracts. We verified 2 upper level functions. We in charge of assignment of pages to a virtual machine. So after very aggressive simplification of the code, which is syntactical simplification mostly, we had just something like 1 line of C code. So it's a very small piece of code after removing all possible, after compressing the code into just a small piece. But in this simplification, we kept all semantic behavior. We just removed some syntactic features which were not, we made some rewriting, which was equivalent basically to the original code. So it is really the original code which is verified, but it is just rewritten slightly. It is an interesting example for teaching, for example, because it is a small example after all, but it illustrates very different features of formal verification, such as function and loop contracts, of course, predicates, ghost code, assertions, lemmas, proof scripts, lemmas proved in Cork, 3 levels of imbricated loops and things like that. So on a very small piece of code, you have very different verification artifact. So the proof takes 5 minutes, and there are something like 500 proof goals, out of which 88% are proved automatically in Pharmacy, either with the internal solver QC or SMT solvers. 11% are proved interactively by WP proof script, which is, for me, for an industrial user, a bad result, because, for instance, in our virtual machine project, we managed to have only 1% of proof goals proved interactively, and 99% were proved automatically. Here we have a high level of interactive proof, and 1%, 3 lemmas are proved in ROC. So I don't know how much time I have. Yeah, but
30 more minutes, I mean.
Okay, so I have time to give some highlights about the main verification issues and aspects we met in this project. I will not show you big specification pieces which can be found in the artifact, but I will try to focus on some intuition on the difficult points and ideas of how we handle them. So interestingly, some simple arithmetic facts were not proven by automatic solvers. In particular, page colors can be computed efficiently using modular and division operations in different ways, and sometimes we have to show that those ways are equivalent. And solvers were not able to handle such operations, so we used arithmetic lemmas. So there are 4 lemmas, 3 of them were proved in ROC. For example, this lemma gives an optimized way to compute the color of the page. It's detailed in the paper, and we have to prove it in code because it was not proved automatically. I think the proof is mathematically relatively natural. You consider a Euclidean division of A by CD and of B by CD, and you simplify and you get the same expression on at the end. But in Coq, it still takes something like 80 lines of proof script. Another difficulty, another feature was ghost arrays. As it often happens, in some cases, solvers have issues to reason about bits. And in this case, we have several bit vectors to represent, for instance, the colors or allocation status. And to solve this, we maintain an equivalence between a bit vector and a ghost array of integers, and define some flattening invariants, making the link between both. And it helps us to facilitate the reasoning on integers in array cells instead of bits, which gives in some way a parallel path for the solver, an easier path to the desired property in some cases. Another usage of ghost arrays was to specify the existence case. So, okay, we want to find a p set in a function. And like, for instance, when we say we want to find an element in an array, we will specify if this element exists, well, we will find it, this one or another one, or if the element doesn't exist, we will not find it. We will return, okay, it doesn't exist. So something similar should be done here. When we look for a p set, when it exists, we want to prove that it is found. And if it doesn't exist, we want to prove that it is not found. However, the difficulty is that in the expression of a p set, as you might remember, there are imbricated quantifiers, and we anticipated that there would be some issues in reasoning about such properties with lots of quantifiers, which would involve interactive proof. Otherwise, we would not be able to deal with existential quantifiers, which would necessarily appear in such a formulas. I remember that I recall that in the p set, we are talking about a sequence of consecutive pages of the same colors. So we have to show that we have a certain number of pages, and there are no pages in between of the same color. So the property is a bit more complicated. So to deal with that, we decided to use a witness as a specification artifact. And basically what we do is that we express the existence case using a witness of a p set. When it is there, we prove that we find a p set. That is, if a witness p set exists, the allocation function finds a p set. But then you will tell me, okay, it is not enough. What happens if it doesn't exist? Because indeed, this doesn't allow us to prove that if it doesn't exist, we don't find it. The specification is not complete. So the solution we used in this case is that we prove in addition that if a p set is found, it was initially present. So in this case, we complete our specification, even with an additional reasoning, with an additional argument, which is not exactly in the proof, but which is easily deduced, because in this way we show indeed the equivalence that, okay, it means that if a p set was not there, it cannot be found. Gauss arrays were also used to prove termination for some functions, to compute the maximal number of steps using a witness in another function. Well, okay, linked lists. It happens that there are also linked lists in this project, and in this, in our case study, we used actually the approach which was developed in our earlier work with a companion view of a linked list, where we introduce a companion Gauss array containing the addresses of the nodes of the linked list, which helps to reason about the linked list, because we maintain a suitable linking predicate between both. And in this way, we can easily express separation properties and semantic properties about the list. Good. Non-trivial invariance for nested loops. Okay, as I said, there are 3 levels of loops in some case. And well, quite naturally, we have to express that to prove that the function finds a p set when there exists a suitable p set, we have to ensure that if such a p set exists, then it is not missed. But interestingly, in some cases, when we proceed in the function, we might be inside the candidate p set, but maybe there is another p set before, so we will not necessarily find the p set, but we should ensure that we will not miss a p set, so we will not go too far without finding it. So this requires some careful invariance for internal loops to specify that the p set is either located in the part of the pool the function has not explored so far, so the p set lies to the right of our current location, or the function is about to find the p set. So the candidate p set is partly inside the witness. So if we carefully express these properties, the proof works fine. Good. What else? Well, as it is often the case in premise WP, which doesn't really use separation logic, and where separation properties should be explicitly stated, we have to express a lot of separation clauses to specify separation of different pieces of memory, which is of course costly. It requires some additional assertions. And in some cases, we have also difficulties in proving preservation of similarly trivial properties through assignments, because which is due to memory models of WP. Here it is explained in detail, but basically we assign a variable, but because of the memory model design, some predicates which don't involve this variable are not proved anymore, are not preserved anymore. And in some cases, we had to design some manually created proof scripts to show that indeed the values in those predicates are not modified, so the predicate remains true. It leads to a verification overhead, and makes also the proofs more complex to maintain. And a proof stability issue in WP was also detected and reported in this effort. Good. The companion artifact, as I mentioned, is available online. So all the scripts and all the annotated code can be found. So to conclude, it was an interesting case study on formal verification of cache coloring in BAO with pharmacy, which is an original industrially relevant and security critical verification target. We found that the code was very elegant, but also challenging for deductive verification despite its small size because of bit-level operations, non-trivial logic, complex arithmetic operations, nested loops, linked list, and so on. So we tried to explain everything in the paper. We found some bugs which were fixed. We proposed some optimizations. And as a future work, we would like to verify optimized version of cache coloring, perform a larger verification of critical parts of BAO with a long-term goal to reach a highly optimized, verified static hypervisor for embedded systems. Thank you for your attention.
Any question?
What are the bugs happened? I mean, actually, what was the problem with the bugs?
What are the exact bugs you mean? Yeah, sure. They have a very similar explanation.
Yeah.
Basically, while moving to the next page or going back to the beginning of the pool to start a full search, the implementation doesn't check the color. The color, there are missing color checks. You can say like that. And maybe it is
as far as I see in
report.
your sketches, I thought that they are checking for the first pages, first page, and then they don't check the continuing checks.
Yeah, so here on one line, we move to another page without checking the color of that page.
Okay.
And in another place, we say, okay, we finished the upper part of the pool starting from the last export location in the previous search. So we finished the part of the pool where we can expect to find enough pages, but if we don't find enough pages, we restart a new search from the beginning because maybe some pages
you don't
have
do
been
checks again.
freed since the last search, and we don't check for the color in this case.
Okay.
So basically, in both cases, we miss color checks. Either we should not move to the next one and stay on the page, the color of which was already checked. It is what we suggested here, but it can be also optimized. Or here we just need to check the color.
Do the color check also checks if the page is used or not, previously allocated or not at the same time?
So each time we check, of course, that the pages are free. This is
In your examples, the second page was allocated already,
right,
but the color was okay.
Right, but it is a side effect of this. Because in fact, what happens is the first page, which is the starting page of the set, is of a wrong color.
Yeah.
And then the pages which are really allocated will be iterated by what is the next page of the right color starting from this page. And that is why in a normal behavior, the first page of the set must be the first returned page of the right color, but in fact, we move directly to the next page of the right color and go also further at the end to another page which was not supposed to be there. So it's a combination of the way it is implemented and the bug which is found here, which makes that, okay, in reality, after all, we allocate bad pages.
There was suspiciously little about caches, actually. So is it how it works that because of the distribution of the pages, you know that you're only hitting the right hardware caches? Because you had like 4 consecutive pages, or I mean, the distribution.
The examples are toy examples. They're not real examples. We implemented them also in this way just to be sure, because we can parameterize by any kinds of parameters. But in real life, I imagine there would be, of course, more, those constants would be bigger. So you don't have just one page of each color. In reality, I think there would be much more pages of several of the same color consequently.
But usually you don't have control over how the cache is used, or very little, right? So I'm wondering how you get from the page level to the cache.
So technically, the color is something like some certain bits in the page address. So you can see the color as certain bits in page address, which are not completely at the end, but which define the color. So the color is actually defined by the address. But it is a bit technical to explain. I don't have a support for that. But to summarize, the color of a page is necessarily fixed by the way the pages are mapped to cache.
Okay.
Are they matched through associative addresses? These are associative caches, very probably, and the colors are the associative addresses that you use to address your pages, aren't they? I mean, if I would be the engineer, I would design like that. That's why I'm asking.
I'm not sure to fully understand your point, but yeah, indeed, when you map a page to a cache line.
Memory location, yeah. So you have some associative address tag in the beginning. It happens to be somewhere in the middle in the original address, but there should be an associative tag in the beginning. And if you map these associative tags, which is part of the memory address, as colors, then you are free to do whatever you want, because all associated caches of that color should also fit into the correct addresses automatically.
We are touching the limits of my knowledge of how it works. What happened here is that we just used the implementation. We didn't have to consider those aspects actually in reality.
So, very nice work. What kind of model do you have of the underlying hardware? Because that might also reflect a bit on the previous question. Do you have a formal specification of the hardware, such that, say, a hardware manufacturer of the processor your BAO hypervisor runs on can also be audited and formally verified with respect to this formal specification?
We would love to go so far, but for the moment, we just focused on the software module. And that's all.
Yeah, nice.
Yeah, so I was a bit surprised. I mean, so it's nice that you find these 2 bugs, but what was the reason why they didn't find these before with testing? Or like, I would imagine that if you do some kind of random testing or property-based testing, that maybe you would also find these bugs. Or is it just that they
are not developers of the product, so we can't say, but my guess would be that you need some combination of conditions to have these bugs.
So it would be like they occur very rarely in practice or something, but it's still.
It depends how pages are allocated, if there are indeed such combinations, which can be achieved by a sequence of allocation and deallocations, but will you really see them in practice so often? Maybe they're not so probable. I can't say, but my guess is that they're not so probable.
Maybe if you never hit memory pressure, it never happens.
That's fair enough, right? So because it's usually much bigger than in these small examples, yeah.
I hope I didn't say some stupid things.
No,
about
not at all.
the
It just it's
presentation
very
because
nice
it's
work,
not
but
my
it's,
domain, so.
no, just yeah. So usually, like you will first implement your software and write some tests, and then hopefully write enough tests to get out all the bugs, and then you do the formal verification. But then it's quite rare that or I would say it's quite rare that you would still encounter bugs while doing the proof. But apparently here it is the case. So
Yeah, we were also surprised to, yeah.
I mean, it's nice. Yeah.
Maybe if you write unit tests for checking your implementation, I mean, you don't think of this case.
No, that's why I said
Yeah.
property-based testing is
Yeah.
typically much better at finding these kind of bugs, because indeed, if you only do unit, so maybe they only did unit tests and no property, like no random testing.
I think the problem is that if you just take unit tests with simple configurations,
Yeah,
you
no.
will never
No, they
find
will
it.
not find it. That's true.
You need complex configurations that you probably will not test naturally, right? And if you need very intensive tests with preambles which generate different configurations, or you will miss them.
I mean, so I know in Rock, for example, people are also quite enthusiastic about this quick check tool.
Yes.
Which if you're trying to proving something, like first try to do some random testing to make sure there's no obvious counter examples before you do all the effort of trying to prove it. And so, yeah, so maybe that would also be useful here actually. So you can, like, because it's like if you had not found that there is a bug, you would be very frustrated, maybe trying to write a proof and not being able to. But it's, yeah.
Would you give the general recommendation that these kinds of algorithms that are part of written in C and part of operating systems, we should be rewriting in pharmacy or looking at more of these?
Well, it is like during our yesterday's discussion during the coffee break, such memory-related modules are critical, and they certainly need to be formally verified, right? Because as we see in this example is a very simple example, but I think any operating system developer will be able to give you other examples where some subtle bugs remain there and are hard to find even after careful testing, code review, or I don't know what. So certainly, I would say, well, I don't know if they have to be rewritten, but at least we have to put an effort on formal verification.
Because you see this trend that now they are rewriting more and more bits in Rust, right? But for Rust, then okay, now you have memory safety, but you don't have the nice proof support to actually show that your algorithm does something correctly, right? You could have implemented the same algorithm incorrectly in Rust, and none be the wiser.
There's no Frama Rust yet.
Exactly.
Probably.
Maybe there should be.
Would this be difficult from a Rust? I mean,
I think there is an effort in this direction, but for the moment there is no version available. So hopefully one day we will have a version, but for the moment we don't.
I saw that BAO is a pretty new project, right?
Yes,
yeah.
it is also a young project.
Yeah,
I
young
think,
project, and it doesn't have so many commercial. I mean, not so many companies are using it, right? I was wondering why you chose it to formally verify it. You think it will be adopted in the future a lot?
The idea was to try to see what exists. It is. I'm not
What
saying
exists
it
for
will
embedded
be
system?
tomorrow an
Ah.
entire product, right? I say we just wanted to see how it works, if we are able to verify to be sure it works properly. So it is a young product, but the need is also relatively young. What I mentioned in the beginning of the talk. Regarding the need for static hypervisors in embedded systems.
Okay.
So it is also something which is relatively recent. And I think there are ongoing efforts to find solutions. to
There
that
are
need.
also many hypervisors for embedded systems.
Well, of course, hypervisors exists
Yeah.
in other
Yeah.
exist in other application domain, but not so much in embedded systems.
As a continuation, do you think this could be done for, let's say, Zen hypervisor? I mean, it's so big.
If time allows, I think probably yes, but with what kind of effort, how many months or years of work, I can't say today, but it would be definitely very interesting. Yes.
So I have the code open here, like it's over 500 lines of specifications you wrote to verify like 80 lines of code. How much effort this took? Like
It was not a very long project. It was maybe a few months. I forgot to put it on the slide, but I think it is written in the paper. Maybe between, including writing the paper, maybe up to 6 months or something like that. Before, yeah, not more than between 3 and 6 months.
did you write all
Roughly.
the specs yourself? Use some automation or?
The specs were written manually, yeah, by the authors, yes.
And how many people were involved in this project?
So the verification effort was mostly conducted by my former colleague Axel, who was writing most of the specifications, but it was also his first project on pharmacy, so we were helping him. So it is hard to say, well, mostly he wrote everything, but we helped him to give ideas and to fix problems and to improve specifications. So maybe we can say that 2 people were working on that, but not full time, but
I thought that many more. It looks very complicated. Yeah.
well, it is not a very complicated project, but it happens that it involves different features and different aspects of different difficulties.
Let's thank Nikolai again.